The next thing we're going to do is to use integration again to calculate the field due to a charged disk. Now we already know the electric field due to a charged ring. So a disk is just a sum of rings with radii ranging from 0 up to a maximum value that we'll call R0, which is the radius of the disk. And if we add up the electric field due to all of those rings, that will give us the electric field due to the flat disk. Now our problem here is to find the electric field due to a charged disk. And the disk we've drawn here, it's got radius R0. Now we want to know the electric field at the point P, which is a distance Z away from the disk. And we're going to build on the previous result where we found the electric field because of a charged ring. And we're going to do that by treating the disk as the sum of a series of thin rings, and each one has got radius R, and that means it has a circumference of 2 pi r, and the thickness of each ring is going to be dr. So the area of each ring, we'll call it dA, is going to be 2 pi r dr, and that means the charge dq on each thin ring is going to be sigma times 2 pi r dr. Now, from our previous problem, we found that the electric field, because of a charged ring, is q times z over 4 pi e naught z squared plus r squared to the 3 over 2. So for this problem, that is going to be the field due to the thin ring, which is z times dq over 4 pi e naught z squared plus r squared to the 3 over 2, which is going to be z times sigma times 2 pi r dr over 4 pi e naught z squared plus r squared to the 3 over 2. So the total field due to the whole disk is going to be the integral of all those dE's, which is going to be the integral of from 0 to r naught sigma times z times r dr. It's 2 e naught because the 2 pi up the top cancelled with a 2 pi down the bottom, z squared plus r squared to the 3 over 2. And I'm going to take all the constant terms out the front, which is sigma, z, 2 e naught, and then our integral of r over r squared plus z squared to the 3 over 2 dr. So I'll continue over the next page. So I've just transferred that last line across to the next page. Now when we have an integral of any x to a power, so the integral of x to the m, let's say, dx, it's going to be x to the m plus 1 divided by m plus 1. So that's the only rule I'm going to use for this integral now. So we're going to say that this equals all our constant terms out the front. And now we have our z squared plus r squared to the minus a half, we raised that power by 1, divided by minus a half, and we have to take that for r0 and subtract it for naught, and that gives us sigma over 2E naught 1 minus z over the square root of z squared plus r squared.